Hello, welcome to my talk. My name is Seongbin, and I'm from Laboratory of Optics and Biosciences in France. And I'm going to introduce NewNet and a Python library called bioimageloader.
So I will first start with NewNet.
And NewNet is not another variant of UNet that we know. It's totally different type of deep neural network. Essentially, is a content enhancing filter, which is generic and self-supervised deep neural network. So we are working on a preprint, so please tune in. So we all know that supervised learning works fairly well for segmenting bioimages, bio-objects. However, when it comes to bioimages, it's hard to get enough ground truth, so in consequence, it's hard to do this supervised learning. And so on your right, I gathered nuclei and cells images from various sources, because of diverse nature of bioimages. It's just hard to come by models that work well on every types of images. So there are models such as Nucleizer and Stardist and CellPose that we know and love to detect blob-shaped nuclei in cells. And if it doesn't work, we can always retrain them on your dataset, on your image. But still, you need ground truth labels to do so. So we propose NewNet here. It is self-supervised, meaning you don't need labels, and it learns implicitly to find a blob-shaped object, so to speak. And because we want it to be generic, we started mixing images from various sources. And as a result, we have a generic filter. Once you have a new image, you can apply NewNet with confidence without retraining your model. But still, because it's a filter, you may need other tools to actually do the segmentation. So just note that. So before diving into NewNet, so I'm going to show you images from LOB, my laboratory. So LOB is specialized in nonlinear microscopy and more esoteric contrast type, various application, and as a result, we have diverse modalities and diverse tissues, and where classical segmentation model often struggle with. So we wanted to have a generic model that could deal with all these different images to segment cells and nuclei. So here I will give you my view about self-supervised learning. So because the notion of self-supervised learning is relatively new and is a very hot topic. And in robotics, they already explored a lot about unsupervised learning. They didn't call it self-supervised. They rarely call it self-supervised learning, I figured. But in natural language processing, self-attention swept the whole community, and everybody started doing the self-attention and BERT and so on, GPT. So they actually kind of start differentiating self-supervised learning from unsupervised learning. And whereas in computer vision community, they kind of took that idea and then start developing what they call contrastive learning, and it got popular over the past years. And actually, so where is NewNet stem from? Actually, NewNet took a very different path to achieve self-supervision from contrastive learning. So it comes more directly from representation learning, such as autoencoder and star transfer. So I will give a brief overview of the architecture of NewNet here. So on your right, we have a pre-trained MobileNet version 2. It's a feature descriptor. We can extract rich features from this powerful convolutional neural network. And we have two losses. First, the contents loss at the bottom is a generative loss, trying to reproduce the input distribution or input image. And for that, we have backup inputs from various sources, including ones from our laboratory, here the X. And meanwhile, the attractive loss at the top attempts to apply a certain style, in this case binary mask-like images that contains blob-like shapes here in S. So after training with these two losses, we now have a generic filter a content enhancing filter. So let's see the result. On your left, we have input. At center, we have output, filtered output, and at right, we have the ground truth. At first, you notice that contrast is improved, so it's easier to find cells in this THD images at center. And the another thing you may notice is from the histogram, you see kind of two poles, so one around 0 and the other one around 1. So the pixels that the neural thing is belong to background, it's pushing them towards 0, and if you think it's a foreground pixels, then it's pushing towards 1. So that's how it makes the contrast gain. So here the contrast was calculated by masking foreground pixels with this ground truth mask. We have more examples here from different sources, because NewNet is a generic filter. It can enhance the content from various sources of images. So once we quantify how much contrast gain we can get from NewNet, here, I mean, we have the two groups, large contrast ratio and this small contrast ratio. They comes from the intrinsic contrast ratio from the images. So comparing before and after NewNet filter, we clearly see the contrast gain here. So another topic that I like to cover is bioimageloader, a Python library to load bioimages for machine learning and deep learning applications. And this is open source, so contribution is always welcome. I hope I can convince you to contribute to this project. So next thing, so while I was developing NewNet, I gathered a lot of bioimages from different sources and needed to manage them and needed to sometimes extend them and manipulate them. And I also wanted to be compatible with popular library that I enjoy using, such as augmentation for data augmentation, and scikit-learn for machine learning, PyTorch TensorFlow for deep learning. And I also wanted to support a new generation file format, entire file format in that matter, in the future. So this is overview of collections bioimageloader currently provides. So which includes many of usual suspects of open science in microscopy. Note that it only provides interfaces to load data, not data itself. So you have to manually go to the source of data set and manually download them. But once you download them, you can easily load them with bioimageloader. So we have currently 28 data set in total, and mainly nuclei and cell images, because that they were what I needed. And I love to support other types of data, so contribution again is always welcome. So this example shows how to use this library. So from lines 6 to 10, you are defining data augmentation, the random cropping and so on. And at line 13, we have a one line to load data science data set. So we can iterate through this data set very easily using for loop and doing machine learning and deep learning. So we have a nice table here. So we can use a bioimageloader to easily do benchmarking. So we have a few popular models, namely Self-supervised and Stardust. And you can see the data set in row and the models in column, and their F1 scores. And you can quickly pick which model would work best for you, your images, for example, from this table. And it's also useful as a building block towards a foundation model. And if you see the last two columns, we have trained a Self-supervised and Stardust model with the dataset listed here. So I will explain what foundation model I meant by. So, okay, the foundation model, some people have proposed the notion of foundation model as one generic model which would be used for many different downstream tasks using either transfer learning or domain adaptation. And so it assumes a large quantity of data, and it needs to cover diverse data in a powerful model and efficient training. So how do we apply this notion of foundation model with bioimageloader and UNet? So with bioimageloader, we can simply load the various type of data from different sources, and then using UNet, we can self-supervise it with no labels. And for the next step, we can plug this foundation to another model, such as Self-supervised or Stardist, and then we can further fine-tune the Self-supervised model to get the best performance out of it. Okay, this is all from me, and thanks for listening. And please tune in for preprint of UNet, and please visit bioimageloader website. And I'm happy to have any discussion in Gathertown. Just be aware that beware of the time zone because I'm in France. Thank you.